I want to start talking about non-interacting Bose gas, Bose-Einstein condensate. So let's start with ideal Bose gas. Remind you, ideal means no interaction, because we are going to be spending a lot of time about interaction. So let's start with simplest. And what we need is wave function. And for that, I am going to assume bugs with periodic boundary conditions. And let's take 3D. And you can think about 2D and 1D as a homework if you want. The wave function is psi r is equal to 1 over b e to the I k dot r, and the k, because of periodic boundary conditions, is determined by 2 pi over L, 3 quantum numbers nx, ny, and z, and the spacing between this k is delta k is going to be 2 pi over L, and V is L cube volume. Now the first thing we need to ask is like, how many states do I have in a given k space volume? So d cube volume contains, so the book is using ms, so let me also use it for s. This is like number of states in a given d cube volume is like d cube total volume, and if you divide the total volume with the spacing of the volume, that's the number of states, right? Spacing is here, d cube is there, this is 2 pi over L cube. Actually, let me write this in 2 steps. So this one is delta k cube. And this one is going to be V over 2 pi cube, because of V, 2 pi cube, E cube k. So this is number of states. And for this wave function, corresponding energy, so typically we want to write things in terms of energy, not the wave vector. So we want to change the variables to energy, and energy in this particle in a box problem is epsilon of k is equal to h bar squared over 2m kx squared ky squared kz squared. And in that case, you can see this is like an equation for a sphere. So constant energy is a sphere. This is like a surface of a sphere. Typically, we show it like this. There's like kx, ky, kz, and there's like this a thin shell, and in this thin shell all states have the same energy. This. All have same. So now we need to calculate number of states at energy epsilon. Let's try to calculate that, and this is by definition energy density of states. So let me write this ms again. So ms is this guy, and let me open this up. So this is, because of spherical symmetry, I am going to open up this d cube k as 4 pi k square dk, and epsilon is equal to h bar squared over 2m k squared. Then d epsilon is going to be h bar squared over m k dk, and k is equal to 2m over h bar squared root epsilon. So let's write these. So this is exactly the same, v over this. I have 4 pi, there's like a k. For k, I'm going to write this. And what remains is k dk, and for k dk, I'm going to write this thing, m over h bar squared d epsilon. And if I collect everything, I have v 4 pi. Okay, let me erase one. This is 2 and this is 2. Actually, let me write it in 2 steps so you can follow. So this is 2. So this one is 3/2. I can erase this. So 1 2 pi is going to cancel this. So this is 2 pi squared. And that's exactly what we call density of states, energy density of states. This is like per volume, because I want to get rid of V2. So this is G of epsilon is equal to this thing. Let me write it 1 over 4 pi squared 2m over h bar squared 3 over 2 epsilon. So we'll be using this in our calculations. And if you plot the, so this is in 3D, and this is 3D box potential. And if you draw density of state, it's like something like this. Just square root. This is G of E. This is E. This square root of energy, yes, this one, epsilon, right? So because I have k dk, whenever I see k dk, I wrote it d epsilon times m over h bar squared. And whenever I see k, that because k dk brought d epsilon here, I spelled this like k dk. K dk brought so this d epsilon, and what remains is k, and it brought like n epsilon, and it's root epsilon. I always get this wrong, so I try to be careful. Now, so this is about the geometry of the problem. It has nothing to do with like particles. Now, if we put like particles like bosons in this case, a given state is occupied with probability given by Bose-Einstein distribution, BE, given by 1 over e to the beta e minus mu minus 1. And here, beta is 1 over kBt. Kb is Boltzmann constant, T is temperature, and mu chemical potential. Now let's write an expression for total number of particles. Total number of particles n is given by, if you sum over everything, you get total number of particles, and it should be sum over k, and this is the distribution. But we cannot do these summations, right? That's why we have to convert it to integral, and that's why we need the density of states. And if you convert it, this is going to be d cube k over 2 pi cube. And let me shift this just a little bit. This is v. And this thing comes out as it is. Or I can write an expression for not this, but like, so this is n. I can take n to v to here. So this is going to be density. So this is density. And this density, as you can see, depends on two parameters. One is T because of temperature there. So this depends on T, and there's also chemical potential. As a function of temperature and chemical potential, this is the density. And now I can convert, right? By using these expressions, we set d cube k here is equal to this square root of epsilon. We can write it in terms of these density of states. And this is going to be, I do exactly what I did there. It's going to be from 0 to infinity, d epsilon, g of epsilon. And this is exactly what it is. And this thing, let me write it, n of t mu is equal to, let me write this 1 over 4 pi squared, 2m over h bar squared 3/2, from 0 to infinity, the epsilon, root epsilon, and this Bose factor. And now I want to make this integral dimensionless. So this is beta, this is beta, and beta is kbt. So I'm going to write kbt times kbt square root is going to be 3/2. So let me write kbt here. Let me try if I can. So this is, so red is I multiplied and divided with the same factor. Now if I, let me copy this so we can follow. If I redefine the variable, beta times epsilon is x, so x is equal to beta times epsilon, then this is going to be dx, this is x, and this one is going to be x times, I want to call it z to the minus 1, and z here is going to be equal to e to the beta mu. Sometimes people call this z fugacity. And what I want to do is, like, I want to multiply with e to the minus x times z, both numerator and denominator. So this is going to be z times e to the minus x. So this is going to be z times e to the minus x, and this is going to be 1. Good. And now I am going to, okay, so let me a little bit nicely. Now I want to write this thing here, z e to the minus x, and sum over p is equal to 0 to infinity. This usual geometric series, z to the p e to the minus px. Or I can absorb this factor inside, and I can start from 1 and I can raise this. It's exactly the same thing. Now the integral I need to take is like this. Take this one, take x, and because z is independent of integral, I'll write it outside. So this is p is equal to 1 to infinity z to the p e to the minus p x. And I do the same thing. I multiply it p and p, and I divide by 1 over p 3 half. Then this integral is dimensionless. This is like some from 0 to infinity du root u e to the minus u. And if you plug this in Mathematica, it is going to give you something like, okay, there's like a function, but let me not write it. So this is going to be, yeah, gamma function, yeah, right? Yeah. But like the nice thing about Mathematica, you don't need to know gamma function. It just integrates these standard things. So it is like that. And the final expression is root pi over 2 some. Let me write entire thing. So this is n is equal to m kbt divided by. I also did the cancellations here, not to be too boring. This is 3 over 2. So this g 3 half of z, where g p of z is equal to this expression p is equal to 1 to infinity z to the p divided by p 3 half. Good. Okay, let's now, okay, so this is the calculation. Let's now try to understand what this is telling us. First, because of this series, g3 over 2z is convergent for z smaller than 1 and divergent for z bigger than 1. And we can also look at the analyticity of this function at z is equal to 1 by taking the derivative. If you take the derivative, dz g3 over 2 of z is equal to p is equal to 1 to infinity p z to the power p minus 1 divided by p 3 over half, and this is 1 over z p is equal to 1 to infinity z to the p root p. And if I put z is equal to 1, is it convergent or divergent, this series? At anything of the form p 1 over p to the s, p is equal to 1 to infinity, is divergent if s is smaller than or equal to 1 because of standard series. So this is, so the series is convergent, but it is derivative is divergent. That means if we want to plot it, it is going to be something like this. This is the function. So this is g3 over 2 z. So this is z, and so this is z is equal to 1. When z is 0, it is 0, and when z is 1, it is finite, and its value is, I think, like what I think this thing is. So let me write it. Push this just a little bit. And g3 half of z is equal to 1 is Riemann zeta function, and its value is, I wrote it somewhere here, 2.612, something like that. The end, what happens is like it's increasing. At z is equal to 1, it is finite, but its derivative blows up. And here, z is equal to e to the beta mu. When z is in between 0 and 1, beta is always positive, is temperature, mu should be negative, right? Mu should be negative. So what we can do is, here is n, here is g, and there's this t factor. Rather than looking at this as a function of z, we can invert this, right? So I can take this axis and invert it like this. Let me write and something like that. Now this thing can be g3/2, and this thing can be mu, right? And there is a point where this e to the beta mu is going to be 1. This is 1, and e to the beta mu is 1. Mu is 0, so here is 0. And below here it's going to be non-analytically going like this. I just took this graph, shifted, and because this is e to the b, there's also some log factors here. So let me now write the expression. So then g3/2 of e to the beta mu is equal to 2 pi. I'm just inverting this. I'm writing the same thing, but leaving g alone. So this is 2 pi h bar squared over m kbt. By the way, this divergence, this point is going to be the signature of phase transition. It is going to be the condensation temperature. That's why I'm spending so much time on this like ridiculous detail. But let's just push forward to see. This is n of mu and t. And this thing, you can see this is like density. So because it depends on n and it depends on t. If t is large, right? Large t 1 over, it's going to be, this side is going to be small. Or if density is small, this entire side, right hand side is small. If this side is small, this side is small. If this side is small, I can expand this side. Right? This is like a power series. I can just take the first and this g3/2 z is approximately z. The first term in the series is z, and z is e to the beta mu. Then I can solve it for mu. So then mu is going to be, I take the log on both sides, and okay, let me write the result: 3/2 kb t logarithm m bt 2 pi bar squared and 3/2. And that's this behavior, right? Here it is mu is equal to 0, and it decays continuously to negative values. Now let's look at the critical point. So this is now after doing this variable, I can write this in terms of t, and this is going to be tc. Tc is the point where e to the beta mu or z is 1. When z is 1, mu is 0. And mu is 0, that's we call critical temperature, and we can write an expression for that. Because, okay, n is equal to, let me write that expression for you to follow. So this thing, okay, here, in the box, so this is n. And at exactly a critical point, z is 1, and this thing is Riemann zeta function is going to be 2.612, something like that. And I can put t is equal to tc at that point, and I can solve this equation for tc. And tc is going to be 2 pi h bar squared over m kb n over 2.612 to the power 2 half. So you can see critical point goes with 2/3 of density. And this is what we call BEC temperature. And below TC, so the question is, what happens below TC? Any suggestions? So at TC, this is what I obtained, right? But below TC, chemical potential is 0. And then what happens? Exactly, right? Like it looks like some like black hole here, but what happens is like all the particles are in the ground state. At least that's what Einstein said. So Einstein's suggestion was all particles occupy lowest energy. Lowest energy is almost 0 because of bugs. It is like it can be finite, but like it is going to be 1 over v. So there'll be like a 0 energy state, and all the particles are in the 0 energy state. And naively, you can think about chemical potential to be the energy you need to give to add or remove one particle, right? That's the dictionary definition of chemical potential. And if the energy to add or remove a particle is 0, that means all particles are in the 0 state. And it is like free to add or remove a particle from that 0 state. Or more precisely, N0 much bigger than 1 particles. So the number of particles in the 0 state, I'm going to use N0, and a large number of these occupy the ground state. Occupy ground state. Okay, let me skip that because I want to do something else. So I want to now think about then, so this N we wrote initially should be written like N0. So this is total number of particles. This is the number of particles in the 0 state and plus all the other particles. So this is K bigger than 0, 1 over e to the beta E minus mu minus 1. And if you do all the things we said earlier, like change this integral from summation to change this sum to integral by using density of states, and convert it to density by using the volume. So what you are going to have is N is equal to N0 plus M kBT divided by, I have these in the notes if you have a hard time to derive it, but they are standard, 2 pi h bar squared 3 over 2 times 2.612. So this one is total density. This one is density of condensed particle, condensate. And this one is density of, we call what is not condensed, we call them normal and condensate. Sometimes when we are studying superfluid, we are going to call superfluid and normal, but here condensate and normal, density of normal particles. Good. And like you can do, like we also found an expression for n above. We can divide everything with n, and what we find is 1 is equal to, okay. So 1 is equal to N0 over n. So this is also standard, so let me just write the result is equal to T over Tc 3 over 2, and Tc is there, right? We found an expression for Tc. This is the Tc, and it is a nice thing to put this equation in dimensionless form. And what you can see here is n0 over n, this object, is equal to 1 minus this object. And that's the important result. And let's sketch that. So as a function of temperature or dimensionless temperature, T over Tc, there is a point where this is 1, and below this point there's almost 0 particles, right? Because it is energetically not favorable to put everything there. And below here it's going to increase, and at T is equal to 0, all particles are on the condensate. So this is n0 over n. And you can see here there is an object which is 0 above a critical point and non-zero below a critical point. And in the vicinity of this critical point, this object or this parameter is infinitesimal, right? Because this is continuously increasing. And what we call this kind of behavior is like order parameter. Just to set the terminology or the jargon, so this is called order parameter. And what we call here is, this is like an ordered, at the moment it is not, but let's just set up the vocabulary. This is like an ordered phase. So this is disordered phase. And these phases are separated by like a transition point, and there's like a phase transition. And because order parameter increase continuously, typically we call this a continuous phase transition, but in the old language, this used to be called second order phase transition. If there was like a jump in the order parameter, people generally call it first order phase transition, because there are things like latent heat and so on and so forth. But this is not important for us. Any questions? So that's the essence of what we are going to be dealing with. So that's quantum mechanics. Here is inscribed by Bose distribution, Bose-Einstein distribution, and as the temperature goes to lower and lower values, Bose-Einstein distribution put all particles in the ground state, and all of the particles are now occupying a gigantic wave function given by lowest available state here. And that's what we call macroscopic quantum phenomena. And we'll see that not this case, this is not quite there yet, but in the case of a more realistic system, this is going to be a macroscopic wave function. Okay, let me tell you 2 more things, and then I'm going to finish after that. So this is we only calculated the density. Other thermodynamic quantities can be calculated. For example, density is not the only thing. We can calculate energy, U, and U is going to be, it's easier to write in terms of K. First K, you have this F, Bose-Einstein of epsilon of K, and it also depends on chemical potential. And if you multiply with epsilon of K, that's total internal energy. And you can also convert this summation to integral, and you can put it in dimensionless form, and you can do this series expansion, and you can find a different form of zeta function. And at the end, what you are going to find is something like that. Let me write the result. So this is optional homework if you want. If you have never done these integrals in StatMech, how many people did these calculations in StatMech? Okay, everybody knows how to do this, right? Then I don't need to spend time. So let me just write the result. So this is 3 over 2 kBT G5/2. Also, it is in lecture notes if you want to derive it yourself, just to test your knowledge. C for T bigger than Tc, and below it is 3/2 Kb T to the 5/2 divided by Tc to the 3/2 is the correct dimension, and this is G. Okay, exactly the same thing, but Z is equal to 1 below. This is T is smaller than or equal to Tc. And from, okay, if everybody knows this, how can I derive, for example, specific heat from the internal energy? Exactly, so this is del U, del T. You take the derivative of energy with respect to temperature, this is the specific heat, and if you look at the specific heat, what you are going to find is something like this. So this is Tc, and there is like a critical point. Let me, there is like, so at very high temperatures, what is like in a three-dimensional gas, what is the specific heat at very high temperatures, like a classical Dulong Petit kind of gas? Like, what's that? Exactly. 3, 2, and Kb. Kbt is energy, but if you take the derivative, Kb, exactly. And this is what it should be at high temperatures. And you come from the high temperatures like this. And when you hit like this critical temperature, there's like a cusp. And this cusp is because of this non-analyticity that we saw in G3, right? In the, like this beginning function has all the information of this non-analytic behavior. And once you hit there, you are going to change the behavior, and this cusp is going to turn and decay. So this is, okay, now it's writing. So this is like a cusp for phase transition. And that means because specific heat is derivative of internal energy, and internal energy can be written in terms of free energy. And if there is like a cusp in the derivative of any object, that means there is like a non-analytic behavior. And if free energy is non-analytic at a point, that signals a phase transition. At least that's what we say in the undergraduate statistical mechanics. And that phase transition is like a phase transition for like a non-interacting Bose gas at low temperatures. Okay, maybe I can stop here. So that's the simplest thing we can do about this. Next, we are going to think about cold atomic gas. I'm going to outline how cold atomic gas is similar and different from this non-interacting gas. And then I'm going to introduce Bose-Einstein condensates of atomic gas next time. And then we are going to move from there.